There are two kinds of boundary conditions in all the problems that we are looking at, and they're called Dirichlet and von Neumann boundary conditions. Dirichlet boundary conditions are boundary conditions on the functions themselves. Meaning that if you have 2 points known as the boundary, let's take one-dimensional problems for examples to fix the ideas, then you only specify what happens at the boundary. So if you have a clothesline strung between 2 walls and you start observing the clothesline on a windy day, you're going to see standing wave patterns like that. Now, no matter what happens, no matter how strong a gust of wind is blowing, you will always observe that the 2 points to which the clothesline is tied will always be a node. And these are sometimes called the anchor nodes. These are called the anchor nodes because you impose the fact that the clothesline is tied between 2 walls a priori. This has nothing to do with what happens with the wind. Now, the wind may create different modes. It may create a fundamental mode which has got no node in the middle, or it may create the first harmonic which has got 1 node in the middle, or the second harmonic which has got 2 nodes in the middle. So the circumstances of the wind will produce different nodes which tie into the different wave numbers that show up in your solutions. So we're not worried about that. That is the circumstance of what happens during the actual problem. These anchor nodes are given before you start the problem. And so those should be considered as the Dirichlet boundary conditions. So for example, if this is x equals 0 and that's x equals L, then the 2 anchor node conditions are that y of 0 at any time t equals 0 and y at L at any time t equals 0. And these completely describe the anchor nodes. So that's a classic example of a Dirichlet boundary condition. And then based off of this, when you put these conditions into the solution of the Helmholtz equation, which in this case is simply the wave equation, basically d2 y over dx squared plus k squared y equal to 0, then you'll end up getting the fact that y as a function of x and t, but the time variable is separate when you do the separation of variables. So really I should have called this capital Y, but I'll just write it as little y. This is going to be a combination of cosine kx plus b sine kx. The first anchor node condition will tell us that, let me call this y tilde. So what I'm doing here is I'm writing y of x comma t as y tilde of x and t of t. I used to call this capital Y in the previous videos, but I lost that chance by writing it as little y, so I'm calling it y tilde instead. Now the first anchor node condition will say that the constant a is 0, and the second anchor node condition will put a quantum number here and will put the value for k to be kn equals n pi over L. That's the quantum number kn. And so this way you can get the full space solution. The time solution can be then got by some other initial condition that you put in the problem, such as some initial velocity that you give it. So that's a classic example of all the PDEs we have done so far, and that's the Dirichlet process. The von Neumann process we are not going to look at in this course, but just to give you an idea of what the von Neumann condition looks like. These are traveling conditions. So you are not going to talk about static processes at the end. You're going to put some conditions that have to do with the movement of the wave or the rate of change of the wave with respect to x. More specifically, these are conditions on the normal derivative. Classic examples come from quantum mechanics. So if you, or even heat theory, if you have an infinite barrier. Now it's the sort of thing that you look at in quantum mechanics a lot when you have infinite potential wells. So if you have an infinite potential well, known sometimes as a square well, then it's got infinite sides and then zero potential between 0 and L, and infinite potential at x equal to 0 and x equals L. Okay, and zero potential here. So there's an infinite cliff on both sides. What you now have to do is you have to impose some sort of a normal boundary condition. You have to stipulate that the derivative of psi with respect to the normal coordinate, which in this case is x, must be equal to 0. Because if it's not equal to 0, it means that there'll be some kind of a flow of probability into the region with infinite potential, and that cannot be true. Okay, so the boundary condition, not on this side, but on this side where there's infinite potential, you have to impose the boundary condition that there's no leakage of flux from here to here. That's one way of thinking about it. So that's the condition you'll put on the function psi. Now, incidentally and amusingly, these sorts of conditions are also done in electromagnetism. Now, without getting into too much detail, electromagnetism is the electric field vector that exhibits these types of phenomena. But you can think of the ray of light as being made up of both electrical and magnetic parts. And focusing just on the electrical part, you can actually derive one of the famous laws of optics by just imposing these boundary conditions. So let me end on that note. Here's theta 1 and theta 2, and here's the wave number vector k1 associated to the wave, and there's a wave number vector k2 associated to the wave. So just a FYI, k equals 2 pi over lambda, and lambda times the frequency equals the speed. Now there is one thing which I want to say, and that is when you go from one medium to another medium, the frequency does not change. The lambda changes and the speed changes, but the frequency does not change. The reason for this is the frequency is proportional to energy by the Planck's constant, and the energy of the wave does not change. Anyhow, so this tells me that the k value is actually proportional to 1 over the velocity. Let me call the velocity, I'll call it c, even though c is a sacred thing. Speed of light, I'll just call it c. Maybe I should call it v, just to be a little bit more general. So lambda times f is v, and because of that, and f is constant, I have k is proportional to 1 over v. Now, for electromagnetic waves, you do have the von Neumann conditions when you go from one interface to the other. The normal derivatives are discontinuous. So k1 in the normal direction and k2 in the normal direction don't match up. But the tangential derivatives are continuous. So you're going to get k1 sine theta 1 equals k2 sine theta 2. Now because k is proportional to 1 over v, I'm going to get sine theta 1 over v1 equals sine theta 2 over v2. Now I'm going to multiply both these sides with the speed of light. C by V1 sine theta 1 equals C by V2 sine theta 2. Another name for the ratio of the speed of light to the speed of light in the medium, speed of light in vacuum to the speed of light in the medium, is called the refractive index. So n1 sine theta 1 equals n2 sine theta 2. So in this manner, by just stipulating that the normal derivatives are discontinuous but the tangential derivatives are continuous, I have derived the law of nature known as Snell's law of optics.